Aloha, Richard Halverson here. This is ITS228, and today is March 10th. And we're going to continue on with binary search trees today. Let me share my screen. All right. Okay, so here we are, and we are here, and today, yesterday we covered trees in general, and that covered binary search trees. And today we're going to cover balanced trees. And then I'm going to give you the assignment I'm going to finish preparing the assignment. The assignment is going to, oh, by the way, I changed this, as you recall. See, this says we have 12 assignments, and actually we have, I reduced the number of assignments. We're actually only going to have 8, I believe. I have to keep these classes straight. What do I have at gradebook class? Yeah, 8. Yes, 8. Okay, so, and we are gonna, next one is gonna be assignment 5. B trees are something different. After assignment, and so assignment 5 is gonna cover both the last chapter, chapter 6, and this chapter 7. All right, so let's go to it. Excuse me, I'm gonna move to a different part of the ship here. Okay, thanks. Okay, let's go to the textbook. So yesterday, let me just hold on a second. I gotta make sure I'm doing the right thing here. Okay. So, yesterday we went into trees, and we covered binary search trees, and binary search trees are nice because they're easy to build. They're easy to build and have them stay balanced, or stay in a way that it's easy to do a binary search using the tree. So I covered all of these last time, I believe, including recursion. I did not cover tries. We're not going to deal with tries. So now let's cover balanced trees. Balanced trees are a special kind of binary search tree. So let's look at it. An AVL, what did I just say? Okay, an AVL tree is a type of that's right, there's 2 types. There's AVL trees and there's red-black trees. I haven't decided which one I'm going to have you implement yet on the assignment, but let's maybe have you do a simple one of each. But okay, so an AVL tree, and by the way, it's just called AVL. I think it's named after some people. Is a binary search tree with a height balance property and specific operations to rebalance the tree when a node is inserted or removed. So it's got this height balance property, and what it is the difference between the height of the left subtrees and the right subtrees is 0 or 1. Okay, so it's balanced in that way. So the node's balance factor is, and that's all the way down. It's all the way down, all the way up. A node's balance factor is the left subtree height minus the right subtree height. It's going to be -1, 0, or +1, and that's and an AVL tree has that property. So recall that a tree is just with just one node as a height of 0. So for calculating the balance factor, a non-existent left or right child subtree is said to be -1. So, okay, right. So if there is no left subchild, then it's like it's -1. That's the height of it. All right, so this shows an example. This is an AVL tree because this one's balanced. You know, this is balanced, and this is also balanced because this is height 2 and this is height 1 here. So this is not balanced because coming up from 3, the distance down to the left is 1, 2, 3, and the distance down to the right is 2. Oh, wait a minute. 1, 2. This, yeah, oh, you're right. Just okay. So this is 2. Oh, it's because of this one. That's right. This is balanced. D is balanced, but C is not balanced. You see, because the left is 2 and the right is 0. So it's got to be 0 or 1. So that's not an AVL tree. So to test an AVL tree, you don't just look at the top node. You got to look at them all the way down and make sure that every node is an AVL. Is balanced like an AVL tree. All right, so here we're supposed to make sure you understand this. Oh, by the way, you should click through this to make sure that you get the points and answer these questions. Indicate whether each tree is an AVL tree. I believe this one is, A is, B is not, and so on. So you can go and you can anyway, you can go and look at those. Minimizing binary tree height yields the fastest searches, insertions, and removals. If nodes are inserted and removed dynamically, maintaining a minimum height tree requires extensive tree rearrangements. Okay, so after it's already built, it's fine. But if you're going to mess with them dynamically, you know, throughout the program, that's what your program does, then insertions and deletions can be complicated. And by the way, that's the advantage of red-black tree. Red-black tree, the balancing requirements are relaxed a little bit, but it makes insertions and deletions a whole lot easier. And the relaxing doesn't affect performance that much. An AVL tree is not as efficient as a you know, a complete binary tree, a nice compact binary tree, but it's not, an AVL tree isn't quite as good as that, but it's not that much worse. So it's close to the same. So we say the algorithmic complexity is the same as with a BST, just a plain old binary search tree. Balance going on. All right, so here, make sure you answer these questions and you know, make sure an AVL tree maintains the minimum possible height. I don't think that's true. And then you can answer these questions too. An AVL implementation can store the subtree height as a member of each node. So with the height stored as a member of each node, the balance factor for any node can be computed in O of 1 time. I just got to look at the 2. And when a node is inserted in or removed, of course, it have to be updated because the height values can be recomputed. So here's an example. So let's say you want to add a 55. That's going to go. It's going to go after this. It's going to go after the 47, but before the 76. So it's going to be a left node off of 76. And so here we see we recompute. Right now it's, you know, balanced height of 0 goes to height of 2, and then the balance factor has got to be computed. So let's just quickly look through this. Look at this. See, the height is recomputed on up, And we got to click one more time to make sure 2 minus 1 is minus 1. Yes, the difference is in the height factors. The balance factor is the difference in the height factors of the two children. So, all right, so click through this, make sure you understand these multiple choice questions. Here's a nice challenge activity. Let's do one of them. Okay, so let's start it up. What is the height of 50? 1. What is 50's left subtree height? Is it 0 or minus 1? I'm not going to get this one right. Let me see what this. Well, I'm just going to guess so we can see what. So it's either. I'm going to say this is going to be 0. Ooh. And I'm going to say this is 1, but I think I'm probably wrong with these. Let's see. Yeah. So the height of the left subtree is minus 1 because there's nothing there. And the height, the right subtree. Okay. So I was looking at the wrong thing, and of course I was off by 1. The height of 50 is 1. So and what's the height of this one? Well, this minus 1 because there's nothing there. And what's the height of this one? That's 1. Okay, so it lets you do it. It gives you another chance. And so let's do it. Let's try this. What is the height of 60? It's 1. What is the height of 60's left subtree? Minus 1. What is the right subtree height? Is 0, I guess. Okay, so anyway. Oh, this is what AVL stands for. Adelson, Velsky, and Landis. Described the data structure in 1962 paper. So you click that, history. So when a tree becomes not balanced, an AVL tree becomes not balanced, then you have to rebalance it. And one of the things there's some things that you can do. One of them is a rotation, okay? And so you can start to see that the algorithms for this, we are given the algorithms, and we are also given the Python versions of the algorithms, and you can see that they get kind of complicated, and red-black trees are similar. So inserting an item into an AVL tree may require rearranging the tree to maintain the height balance. You know, and the purpose of, you're really supposed to like learn the algorithms, but it's really nice to go through these animations because then you see how the algorithms work. And then when you're looking at the algorithms, you kind of know, how it's supposed to work, and you can see how the algorithm describes something that you already know how it's supposed to work. So here's a simple rotation of an AVL tree. This is going to be a right rotation. So it's like the 70. It's like it rotates, and this becomes the root, and this becomes a left subtree, and a right subtree, and this becomes a left subtree, just like this here. See, so if we see that it's imbalanced to the left, we do a right rotation, just like that. So you can drag here. This is what it's going to look like when it's done. You're supposed to say what nodes go in what positions. That's pretty easy. You can do that. Right rotate, the B's form a right. Okay, so below. Okay, so sometimes these nodes might have subtrees. So here, this, we have to do a right rotate. So D is going to become the right subtree of B. But what do we do with C? Well, C needs to be in between B and D, because C is in between B and D in value. the key value. So it's got to be put in between C. It's got to be put in between B and C. D is, we see D takes up the right subtree, but then C is going to be put, and D doesn't have a left subtree. D doesn't have any subtrees, so we will just make C a left subtree of D, and that'll make in between D and B, and we can see that. See, first it rotates like that. Oh, that's how that works. And here is another participation activity where you're supposed to visualize where these things go. So so remember, 29 has got to go in between 27 and 53, and 53 is not going to have any children. So let's instead of 27 being the right being a right subtree of 27, let's make it a left subtree of 53 after the rotation. That frees up the right subtree of 27 when it becomes the root. So 27 is now the root. We know that, N1. And 53 becomes N3. And 29 becomes N4. See, so 29 becomes N4. And then, of course, 9 still remains the left subtree of 27 and 2. All right. So and then there's, of course, there's left rotates, and this thing is imbalanced on the right, so we got to rotate left, and we can match up what these are. Well, so what's going to happen? 60 is going to be at the top, and 51 is going to be the left subtree. 51 is going to be the left subtree of 60. 51 is not going to have a right subtree, so 57 can take that place. So we have 60 being N1, and we have N2. N2 is going to be 51, and you can finish that. So now we're going to go over the algorithms that support AVL trees. There are these, you know, we're going to have insertions and removals, right? We're going to insert a node, and when we're done inserting the node, we want it to still be an AVL tree. And when we remove a node, we want it to still be an AVL tree. And these insertions and removals, they start out with regular old tree BST insertions and removals. But after we do the regular binary search tree insertion or removal, we have to check to make sure it's still an AVL. And if it's not an AVL tree, then we have to do all this other rebalancing stuff. Okay. And to help us with that, we have these algorithms here. We've got we have an algorithm that updates the height, the node's height, by taking the maximum of the child's subtree heights and adding 1. This is good here because it clears up any sort of ambiguities you may have had in any of these terms. AVL tree set child algorithm sets a node as the parent's left or right child. So and it updates the child's parent pointer and updates the parent node's height. And so we see, you know, remember when we talked about trees in the last chapter, we talked about some trees may have a parent link, and we see that in AVL trees, it's very, very useful to have, very important that we have a parent link. And AVL tree replace child replaces one of the node's existing child pointers with a new value, and then utilizes this AVL tree set child, utilizes this algorithm. And AVL get balance computes the node's balance factor by subtracting the right subtree height from the left subtree height. So these are how these algorithms work. And course, you know, you just converting this to Python is easy. You should be able just to look at this and convert it automatically to Python. You know, the algorithmic language uses these curly braces, which actually enclose the block. But in Python, we don't have those. We simply indent to indicate the block. The block is the indentation of this above it. And then once we go back out here again, it's the end of the block. Also, we have, you know, null is none. This is a little dot there and so on. So you can pretty much translate that. So this is update height. This is set the child. And you can look at the, okay, so this is update height. So it looks at the left. Well, actually, it's better if you go through these exercises, so you really have firmed up how these algorithms work. And then you go over here to Python AVL trees. And we should be able to see them here, I believe. Rotate, here's rotate left and rotate right. This is rotating left and rotating right. And then we've got the rebalance here. Look at how pretty complicated. Insertions, removals. And then of course down here we've got the implementations themselves, and we can actually run it. And so, you know, I'm going to have you implement some of this. All right, so anyway, I just want to show you that. Let's go back to where we were, which was insertions, I believe. Yes, here's where we were. AVL tree get balance is a precondition for it has a precondition that the node parameter is not null. Get balance. So the node can't be null because it's got to have a left. It's got to have a left node. And you got to be able to test if the left node is null or not. You have to be able to test if the right node is null or not. And if it comes in null, it doesn't have any of those things. So you get some value error or something. And so I would say that it's true. Yeah, right, okay. AVL tree get balance has a precondition that the node's children are both not null. I don't think that'd be a precondition, because you can have null, you can be a node without a left child or a right child. Let me see. Tree get balance. No, because it tests if they're null or not. See, so it takes care of that. So this is false. Yeah, all right. So this is the concept of preconditions. That's a computer science concept. You know, we if you were well, you determine preconditions for loops and invariant, you know, that it's looking at those things that you use to prove that your program runs correctly or you know, covers all the cases. If you identify the precondition, then you can make sure that those preconditions are met before the algorithm executes, and then that makes it more robust. All right, so make sure you understand what all this means. Here's the right rotation algorithm. Okay, here's the right rotation algorithm, and the right rotation algorithm is defined on a subtree, which must have a left child, because it's got to have a left child, because the left child is going to become the new root. So a right rotation means you're going to have a new root, and the new root is going to be the left child of the root. So the algorithm reassigns the child pointers, assigning B's right child with D and assigning, okay, here, so, okay, so subtree root, we do, no, okay, so we don't necessarily do rotations on the root node. We can do rotations anywhere. In fact, we have to be able to do rotations anywhere, because we might have to rotate something down below before we can rotate higher up, because there's got to be a place for like if you're doing a right rotate, there's got to be a left subtree, but that subtree so my timer, what was that for? Oh, that was yesterday's class. All right, so anyway, instead of my trying to explain it to you, it's a good idea just to go through this. And so we see here, we're going to rotate D. Okay, we're going to rotate D. And so D is going to go down to where T4 is. No, so B is going to take D's place, and D will become the left. D will become the right child of B, and we see that, but B has got a right child, so D will no longer have a left child, because the left child was B, and B's not the left child anymore. B's a parent, and so C can become D's left child. And so that's what we see here. And we also see that these leaves just stay where they are. This is the left child of B, left and right of C, and the right child of D. Okay, so refer to the AVL tree rotation algorithm. The algorithm works even if B's right child is null. Okay, so if B's right child is null, it should work, because we just don't have to worry about C anymore. Is that correct? True? Yeah, D's left child pointer will simply be set to null. The algorithm works even if D's left child is null. Okay, D's left child is null. No, it can't work, because then we can't do a right rotate. There's no node there to take over the top D's place. There's no node to take over D's place. So this is false. All right. So when an AVL node has a balance factor of 2 or -2, in other words, it's not in balance anymore, one side is more than one different than the other side, it only occurs after an insertion or a removal. The node must be rebalanced. So this is just any node. Once, could be way down there. If there's a removal or an insertion down below there, it can make that node be not balanced anymore. So it's got to be rebalanced. So the AVL tree balance algorithm updates the height value at a node, computes the balance load factor, and rotates if the balance factor is 2 or -2. So first it does a rebalance, and then it knows if it has to do a rotate or not. So that's what this algorithm does. Checks the balance. If it's -2 or +2, then it's going to do. If it's -2, it's going to do rotate right. If it's +2, it's going to do a rotate left. All right. Anyway, so you can confirm in your mind that that works. Let's do the first challenge activity here. So given the following binary search tree, violating the AVL property balance, AVL height balance property. So we're going to rotate at node 63 is going to rotate right, and 84 and 75 become okay. So right rotate at node 84 yields this. Yes. Okay, you can do the rest of them. Okay, here's an example of insertions requiring rotations to rebalance. Inserting an item into an AVL tree may cause the tree to become unbalanced. So, and then you got to do a rotate. So here we have, you know, this height is 0, this height is 1, and so this height is whatever. Yeah, and so after you add A, then you gotta recompute that, recompute that, and it becomes 2 because this is 2 and this is 0, so this becomes 2. And then so we want to rebalance. We want to rebalance at B, and B becomes C, and that's all we got to do. See here. So let's see. So we rebalance. All right. So sometimes a double rotation is necessary to read a double rotation. So here we do a double rotation. First, we have to rebalance A, B, and C. First, rotate left at A. Oh, we rotate left at A. Oh, okay. So first we're going to rotate this, and B becomes B. Oh, it's rotate left. So B takes A's place, and A becomes the left child of B, which we have here. And then we rotate, start here, and we rotate at C, we rotate right, and B takes C's place, and A remains the left child, but C becomes the right child of B, like this. So if we take a look at that, see, if we just do a single rotate, we still have a problem down there. So instead, we're going to do a rotate down there, and then another rotate here. See. All right. So, and you have to be able to detect how that works. So you can go through this. It looks like there's going to be a double rotation, left and right, and then when performing a double rotation, first a left rotation, then a right rotation indicates each node's new location. And so after the initial left rotation, where is Y? Okay, so the initial left rotation is going to be left. So I guess Y and X sort of trade places. No. Y becomes where X is, and X becomes the left child of Y. So where is Y? Y would be N4. N4. Okay. Y. Y becomes N2 and X becomes N4. It's X that becomes N4. So this goes up to there, and this goes down to there, and that's X is, and Y is up here. So Y is rent 2 is, all right, I messed up on that. Excuse me, stop this. There we go, stopped. So that's correct. Let's do the next one. After the initial location, where's X located? Okay, that would be N4. Okay, so anyway, you can finish those. So here, there's 4 different ways that after inserting a node after inserting a node on the path from the new node. Okay, after inserting a node, nodes on the path from the new node all the way up to the root should be rechecked for a balance factor of 2 or -2. So the first such node, P triggers rebalancing. Where does P come in here? Okay, well, anyway, so the four AVL imbalance cases are possible. Four cases are possible. So let's just run through this and see what this tells us. So that's insert a node, and we get that, and we get, that's the left case, the left-right case. Yeah, don't tell me the right-left case and the right-right case. The left-left case, the left-right case, the right-right case, the right-left case. Okay, so those are the 4 different cases that can cause rebalancing, and 4 imbalance cases in rotation. So this is the how it's fixed, I guess. Now this is how they're fixed. The left case is just considered, you just do a 1 rebalance, but if there's a left-right case, you need to do a okay, so if it's a left case, you just do a right rebalancing. If it's a left-right case, first you do a left rebalancing, then a right rebalancing. If it's a right, it's just a simple left rebalancing. If it's right-left, you do a right then left. Very interesting. Okay, so you can go through these to make sure you understand what these balance factors. Let's do one. Okay. In A, the balance factor is, see, it's left -2, I guess. It's 2, and W's balance factor is 1. 1 minus 0 is 1. Is it left minus right? Okay, I think it's left minus right. So it'd be, I'm going to say it's this one. Yes, it is left minus right. All right, you can figure that out. Insertion with rebalancing. So an AVL insertion involves searching for the insert location, inserting the new node, and updating the balance factors and rebalancing. So the insertion is just like with the binary search tree. Okay, but then after that, you gotta do the balancing thing. Balance factor updates are only needed when the node's ascending along the path of the inserted node up to the root. Okay, so it only affects those nodes all the way up to the root, and each node's balance factor can be recomputed by determining the left and right subtree heights, and for speed can be stored in each node and then incrementally updated. So incrementally updated. If the ascending from the left child, then -1 if it's ascending from the right child. And if a load balance update yields 2 or -2, then we know we know we're in trouble. We have our work ahead of us. So here's an example of using a phone book if you wanted to think of it that way. The four insertion cases, and that you can just do increments. If it's in the left or the right, or so on and so on. So make sure you understand that. So here is the algorithm expressed. And so you can step through that and answer these participation activity questions to make sure you understand the insert algorithm. So the rebalancing comes down here. The first part is just inserting into a, so if the root is null, then it's the first node. Otherwise, the current node is the root, and then we, while the current node is not null, if the node that we're trying to insert is less than the current key, we go down the left, or if it's otherwise, see if it's null, then we just add it, and so on. And same with the right, similarly with the right, and when we're done, we see if we have to rebalance. So so you can go through these. Let's see. Let's do this one. Insertions. Okay, so it looks like everything's balanced. This is balanced. This is balanced. This is balanced. This is balanced, and this is 2 and 2, so it's balanced. Inserting which nodes would unbalance the tree? Well, where would 3 go? 3 would go boom, 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 over here, so that would definitely unbalance it, because 3 and 2, this would be, oh, it would unbalance this, it would unbalance 20. Inserting 3 would unbalance 20, because 20 would be 2 on the left and 0 on the right. So this would cause an unbalanced AVL tree. How about 19? 19 would go here. Yeah, 19 would go. 19 would be added as a right child of 10. So that's just like adding a 3. How about 23? Now 23 would be added as the right child of 20, and that doesn't affect the balance of anything. 32 would be added as the left child of 38, so that would make 45 not be balanced. And 41 would be the right child of 38, so that would make 45 not be balanced. 54 would just be added to 45, so that's okay. I wonder if I got this right. Yes. Yes, okay, and you see, adding these things did not affect whether 30 is, whether the top one is unbalanced. The top one seems to remain balanced because we're just adding one to this chain or adding one to this chain, and these two are equal. So it would at most make this one be -1 or +1, but it's this one. It's the subtrees off of the root. Anyway, okay, so here's removals, and you know, this is the same sort of issues here. Like here, we're going to remove 63, and so then it's not. So then 61 is not balanced. So we gotta, you know, do a rotate thing where 21 takes this place. Let's see what this looks like. So we're going to remove that one, and we do a rebalancing. And then what are we going to do? Remove 84. Yeah, okay. Oh, I see. And then we do a rebalancing. Okay. All right. So that shows how that works. So BST Removal Algorithm is used as part of the AVL Removal tree. Yeah. First it does that, and then we got to rebalance. After removing a node from the AVL tree using the standard BST Removal Algorithm, all nodes must be rebalanced. No, it's just going to be the ones from the removal from the node that lost its child up to the root. So I'm going to say it's false. Only the removed node's ancestors from the parent up to the root must be rebalanced. So here's the algorithm. And so here we just remove the node like a regular binary search tree removal. I guess first we search for it using binary search tree search. Then we remove it, and then we have to do the rebalancing thing. So you go through this. This is the rebalancing algorithm, and this is removing a key. You just remove it. Simple. And so the complete algorithm is here. So here's a nice participation activity. Oh, and worst case scenario, traverses the tree from the root to the lowest. The worst case, the AVL removal algorithm traverses this tree from the root to the lowest level to find the node, and then removes it, and then it traverses all the way back up to the tree to rebalance. So the node, one node is visited per level, and at most 2 rotations are needed for a single node. Oh, okay. See, you learn things by reading this. At most 2 rotations are needed for a single node. Well, that's good to know. Each rotation is O of 1, and therefore the runtime complexity is O of log n, because it's the distance that it's got to travel times 2. And each time it visits a node, it might have a lot to do. It might have to do a couple, it might have to do a couple rotations and stuff, but still it's O of 1. And so let's see what this looks like. Select the order of the tree altering operations that occur as a result of calling AVL tree to remove 70. Okay, so we're going to remove 70. Okay. And I guess say so the nodes. Okay, select the order of tree altering operations. Okay, so the first one is $73 is copied into the root node. I think that might be the first one. Okay, tree. No, tree's root pointer. The tree's root pointer is set to the tree's root pointer is set to the root's left child. No, that's comes after it's found to be 89. The node being removed is compared against the tree's root and is not equal. 73 is found as the successor to 70. Okay, that has to happen. 73 is, okay, so I think it's this one. First, you have to find the 73. First, you have to find 73. And then 73 is copied into the root node. Okay, so this first one, I think, is this one. Yeah, okay, well, you can do the rest. All right, now we discuss Python. And these are Python versions of all of the algorithms that we've seen so far. And so you will have plenty of time to learn this, because I'm going to have you just implement it. Just get this thing running down here. This goes through all the Python versions. Make sure you understand the specific Python versions of the algorithms. No curly braces. There's just a colon here, and then everything's indented. and insertions and removals, and search and remove. And here are the here's the code. And so we are AVL tree node. So it's just 3. The AVL tree is this. And so in here we've got from tree print. Okay, so this is something else. And what is, okay, that's tree print. Okay, let's see what it's got. The node class, init, get balance, get height, set child, replace child. This is AVL tree. Rotate left, rotate right, rebalance. There's a long bugger. Insert, search. This is just searching a binary search tree. And okay, so we will be implementing those. All right, so take a look at that. It's nice to understand the algorithms before you actually get the code running. I'd like to just go through a little bit with red-black trees, and you can read this too. It's just as, after you've been through the AVL trees, you can read this, and it's just describing another technique that came up. Somebody came up with this, and it turns out that when you use red-black trees, they're like AVL trees, but their insertions and deletions aren't as complicated. And you've got names for a bunch of these things. You've got red children and black children, and you've got uncles and all kinds of stuff. It shouldn't be uncles. Yes. It's not a generic term for aunt and uncle, is there? A non-gender term for aunt and uncle. But so the rules of a red-black tree are: every node is colored either red or black. The root node's always black. The children, a red's children cannot be red. A null child is considered to be a black. A null child is considered to be a black leaf node. All the black leaf. Okay, so at all paths from a node to any null leaf descendant node must have at least the same the same number of black nodes. So it's a bunch of rules like this, and somebody figured out that you know, if you follow these rules, and then when you do insertions and deletions, you maintain these rules, it's really easy to maintain the rules. Okay, and you relax the height and balance a little bit, and it ends up almost as good. And you can actually search on red-black trees if you want to. It's probably easier because this textbook does a horrible job of telling you why you're learning this stuff. It's not until you get to the implementations that you can perhaps get a clue that it's easier. You just implement these methods, which are all real simple, and it ends up being a lot simpler. And so I'm going to go through this carefully. I haven't designed the assignment yet, but it'll be there before the next time, before the next class next week. I think I said yesterday, I think I said something different about when I was going to have this assignment ready, but since we're doing assignments every other week now, I think I should probably combine all these trees. This is all about binary search trees and variations of binary search trees. I haven't decided yet whether I'm going to ask you to implement the standard AVL tree, which everybody knows. Frankly, red-black trees, I just heard about these, you know, when I agreed to teach this, when I decided to teach this course and use this textbook. There's an interesting let's see, where did I see there? AVL removals. Somewhere at the end of one of these, there was a okay, so I'm sorry, I want to find that one. AVL Trees. I thought it's a great animation. It's at the end of one of these things. I don't think it's at the end of this one. I gotta find it. Here, AVL Tree Simulator. Okay, this is great. Here's AVL Trees. They got all kinds of them. Okay, all kinds of visualizations. You can see how these things work visually. Let's do this. Okay, so I'm going to insert a 10, and there's a 10. I'm going to insert a 15. It goes there. I'm going to insert a 8. It goes there. I'm going to insert 7. Goes there. I'm going to, oh, did it? And I'm going to insert 6. Okay, there it rebalanced. You see that? Anyway, isn't that cool? And that is at the end of section 7.3. Okay, so let's try to remember that 7.3. Let's see, it's 10:15. That's all I had for today, and I will see you next week. First thing we'll probably do is go over the assignment, because then after that we're probably going to want to dive right into the next chapter, which is heaps and treeps. I like heaps. I like heap sort is my favorite sort. So anyway, I will see you next week. Thanks for watching.